Developing a major mine requires an upfront investment of several $billions before the first ton of ore is sold. Companies deploy fleets of excavators and haul trucks to reshape mountain ranges based on a series of underground estimates. Because the Earth's crust is opaque, drilling is the only way to confirm what lies beneath the surface. Poking holes into a landscape blindly is an expensive exercise in trial and error, where every empty drill hole represents lost capital. A financial loss is manageable, but hitting a hidden structural hazard is catastrophic. If an excavator strikes an unknown fault line or a pressurized water pocket, the result is a total operational failure. To manage the costs and risks of the underground vacuum, engineers need a method to see through solid rock before excavation begins. This requirement created the field of mining geophysics. In the limestone regions of Java, the surface often appears perfectly stable. A site might look ideal for a new pit, but the geology tells a different story. 10 meters beneath a 100-ton excavator, a hollow karst void could be waiting. If the equipment weight exceeds the ceiling's strength, the ground will collapse without warning. Ground-penetrating radar maps these empty spaces. It shoots high-frequency waves into the soil, which return as a distinct differoxy hyperbola upon hitting a cave. By analyzing these shapes and blanking zones, engineers pinpoint the hazard's location to safely adjust the mine plan. In limestone environments, interpreting a radar signal determines the stability of the entire pit. Identifying a void before the ground collapses allows engineers to reroute equipment and prevent a fatal accident. Geophysical instruments do not work like cameras. They never see the minerals directly. They only measure how the Earth responds to physical stimuli. The science of rock physics explains how different geologies leave unique physical fingerprints. Geologists look for variations in density, magnetism, and electrical resistivity to identify potential targets. The danger lies in a concept called non-uniqueness. A single anomaly, like a massive spike in density, is not a guarantee that a trillion-dollar ore body exists in that spot. Nature is often ambiguous. That high-density signal could represent a concentrated vein of gold, or it could just as easily be a useless block of barren granite. On a computer screen, they can look identical. Without geological context, geophysical data is just expensive noise. Relying on a single measurement tool to make a billion-dollar decision often leads to failure. To eliminate the problem of non-uniqueness, geophysicists use forensic integration. By stacking different physical measurements, they force the true nature of the geology to the surface. A typical workflow layers magnetic maps, resistivity, and drill assays into a single 3D block model. The physical assay acts as the anchor, providing ground truth to constrain geophysical interpretations. This resource classification model tells engineers exactly where minerals are, their worth, and where to build mine walls. Certainty underground is a product of engineering. It is built by mathematically interlocking physics, geology, and physical evidence. Once the digging starts, the mountain becomes a dynamic system. Moving millions of tons of rock changes the water table and creates new stresses in the remaining walls. Operators use time-lapse geophysics to monitor changes. Scanning the same ground repeatedly reveals how the mountain's internal structure moves over months. Comparing a new scan to the baseline Sibylum Operacy reveals invisible changes. Sudden resistivity drops indicate a zona lama, or hidden water seepage. These periodic scans allow engineers to detect a toxic leak or a structural shift long before the failure reaches the surface. This proactive data stream is a requirement for modern environmental and safety standards. In the operational phase, geophysics provides a continuous stream of data on the internal stability of the mine. The focus moves from discovering value to maintaining a safe environment for the workforce. The next step for the industry is the digital twin. This is a virtual wireframe version of the mine that is updated in real time by continuous geophysical data and time-lapse scans. This system changes how risks are managed. Instead of reacting to a visible crack in a wall, algorithms can flag microscopic fractures and pressure changes as they happen, allowing for immediate intervention. Before humanity can safely extract resources using heavy machinery, we must first use physics to listen to what the Earth is telling us.